Hello there and welcome to Quarantine Ballistics. As you probably know, I set up a small lab inside my house so that I can film videos more often than before, even during this bloody quarantine. Anyway, today we've got an old Springer airgun, which may seem not so exciting at first, but what if I tell you that this technology can shoot faster than any other, including firearms? That would probably surprise you, considering that these usually shoot slower than 300 meters per second, while firearms can exceed 1000. So why is it? First of all, let's have a look at how this thing works. This is an old and beaten black barrel Springer airgun, which you probably have all already seen, but I'm going to tell you something most of you don't know about it. Let's start with the basics. I have already removed the stock, and you can see that when the barrel is forced to tilt, it moves this arm backwards, forcing it to compress a pretty robust coil spring. I want to disassemble it fully to see everything in detail, so I am removing this screw, which acts as a pivot point for the barrel to rotate, unlocking the mechanism and allowing me to remove it. Now we can focus on the rear part, which is where the magic happens. As in many other designs, in this particular one the trigger group also acts as the plug that keeps the tube closed, thanks to this pin, which I am now removing. Now the airgun pros use a piece of equipment similar to a bow press to avoid the spring being suddenly released. I don't, and this time I didn't even swear doing it. Fuck. Anyway, we're getting to the core of the system, the spring and the piston. As most of you know, when you cock the rifle you're not compressing any gas at all, but only the spring. The rearward motion of the cocking arm pushes the piston at the end of the stroke, where its tail engages the trigger sear. Air is only compressed when the trigger is depressed, and the piston is allowed to move forward. Pushed by the spring, it quickly accelerates towards the breech of the gun, and with its top face being provided with a gas seal, it compresses and therefore also heats the air contained in the cylinder. Through a small port, the compressed air can then enter the barrel just behind the pellet, pushing it and shooting it out. And now for the not so obvious things. First, the piston reaches the end of its stroke long before the pellet exits. In fact, it typically tends to hit the bottom when the pellet has only moved somewhere between 4 and 8 inches depending on the particular configuration. The impact also causes strong vibrations, which are detrimental to accuracy and are the reason why Springer airguns are known to break scopes unless a specific shock-absorbing mount is used. Second fact, the pellet can start moving when the pressure is still quite low, and this is the biggest source of inefficiency of the design. The initial movement of the pellet decreases the maximum pressure reached, which is typically between 50 and 100 bars. Third interesting fact, the air reaches temperatures typically between 600 and 800 degrees Celsius at peak pressure due to the near adiabatic compression. But how is something like this supposed to shoot faster than a firearm? To understand these more easily, together with a very important mechanical principle, we should go back to an even simpler weapon, the slingshot. Let's imagine that you want to design a slingshot, having an infinite supply of natural rubber with unlimited force to pull it and draw length, and that you want it to shoot as fast as possible. You would probably watch a few videos on the slingshot channel, finding out that a well-made slingshot can shoot a little over 100 meters per second. At that point, you could simply add more rubber, more draw length and more force to pull it, use a lightweight projectile,
let me show you its features,
and would find out that the velocity you're getting is pretty much the same as that of your slingshot.
Thanks and bye-bye.
The best way to understand this is to follow an energetic approach. Consider that when you stretch a rubber band, or a spring, you are essentially storing potential energy in it, which will be converted into kinetic energy when you release it. That kinetic energy doesn't completely go into the projectile though, but also into the elastic band itself, since it has to accelerate as well to be able to pull the projectile with it. Same thing happens with guns. The elastic band is replaced by some sort of high pressure gas, but the same reasoning applies. That gas, in order to keep pushing on the base of the bullet, has to be accelerated as well, thereby preventing some of the available energy from going to the bullet. In detail, while the end of the band or gas column moves at the same velocity of the projectile, the other end stays still, so the kinetic energy given to the band itself is not shared uniformly along the length. In this regard, it can be proven that the kinetic energy needed for accelerating the gas is 1/3 of what would be needed to accelerate the entire amount of gas to the bullet's velocity. We therefore say that the propellant has an equivalent mass of 1/3 of its real mass. Now let's go back to our slingshot. Let's say that with this current setup, the elastic bands weigh 3 grams and we're shooting a payload of the same weight at 100 meters per second at full stretch. In order to increase the velocity, we need to provide more energy, which means using more rubber. Let's now say that we do a 4-fold increase in the rubber amount. Now we store 4 times the potential energy into the full stretched bands, but we also increase the mass that has to be accelerated. Remember that the equivalent of 1/3 of the propellant mass has to be accelerated to the same velocity as the projectile. This means that even though we now have the energy of 12 grams of rubber instead of 3, it has to be distributed over a larger mass. Originally, we had the energy of 3 grams of rubber divided between the 3 grams of payload and 1 gram equivalent of rubber. Now we have the energy of 12 grams of rubber divided between the 3 grams of payload and 4 grams of rubber. This would translate into a velocity of 150 meters per second, corresponding to a roughly 2-fold increase in kinetic energy for a 4-fold increase in potential energy. This means that our ballistic efficiency was just cut in half. What I have just said applies to guns as well, and in fact you can find this same reasoning in chapter 9 of Corner's book on internal ballistics. Even assuming you could design a gun however you want to make it shoot as fast as possible, as you add more and more propellant, the velocity will tend to stabilize towards a limiting value, some sort of ballistic speed limit which only depends on the propellant itself. The difference, of course, is that 1 gram of smokeless powder, even accounting for thermodynamic losses, can provide about 250 times more energy than 1 gram of rubber. The closer you get to the limit, the harder it gets to go faster, with ballistic efficiency nearing 0%. Now, as you approach the limit, the equivalent mass rule is no longer accurate, weird things start happening in the gas column, and more sophisticated theories are needed for predicting the exact theoretical limit velocity. In practice, however, there is no way you can exceed 2000 meters per second with any solid propellant, and no existing platform goes beyond 1700. The limit is in the propellant itself, with its energy density being limited by chemistry. And here's why airguns are at an advantage. With them, we are no longer constrained by the chemistry of the propellant and are allowed to use any gas that we like, which is very useful. You see, the ballistic speed limit for a gas is directly proportional to the speed of sound in the gas itself, which depends on its temperature and molecular weight. If we want to reach a high velocity, we need high temperature and a lightweight gas. With firearms, we could only get it hot, while with airguns we can get both, using a light gas like hydrogen or helium and compressing it rapidly. This very specialized type of airgun is in fact called a light gas gun, and allows reaching velocities up to 8000 meters per second, or almost 5 times faster than the fastest tank saber round, while being basically just a glorified piston airgun. There are 3 reasons why I decided to talk about this today. The first is exploring the science, understanding the concept of ballistic speed limit. The second is that, like many of you, I'm bored. And the third is that I am actually building a light gas gun, which I will document in upcoming videos, and I'm doing it for very practical reasons, which you can try to guess in the comments, but I will not disclose yet. Anyway, since you are probably having a lot of free time as well in this period, here's a quick riddle for you. Why do you think I picked a Springer airgun and not a PCP? Let me know in the comments. If you have watched all of the video, you already have all the necessary knowledge to answer. And finally, I'd like to remind that any video content that is even remotely linked to guns gets totally snapped by advertisers, rendering the making of these type of videos economically unsustainable. The reason why I can keep investing in producing this type of content is because of the direct support I get on Patreon, which unfortunately is nowadays the only way to provide information and education with freedom of speech. So thank you very much Carson Polar, Robert John Madry and my other 6 patrons, which are as usual displayed at the end of every video. Thank you all for watching, subscribe if you'd like to see more, and I'll see you next time. Bye.